On the 2nd of January 1982, a farewell run from London King's Cross to Edinburgh marked the end of the British Rail Class 55. As the locomotive pulled away, it silenced a deafening, blue smoke trailing scream that had dominated the East Coast main line for 2 decades. This was no ordinary railway machine. Inside the body shell sat the Napier Deltic, an 18-cylinder, 36-piston, 2-stroke diesel engine with no valves, arranged in a bizarre triangular layout. It sounded more like a low-flying bomber than a train. For years, it allowed British Rail to tear up the timetables, setting a relentless 100-mile-per-hour standard. But the paradox of the Deltic was that it did not die because it lacked power. It disappeared because it was too complex for a standard railway depot to keep alive. When a Deltic broke, fitters could not easily repair it. The entire block had to be pulled out and sent back to a specialist factory. But the real story of the Napier Deltic is not only the story of a retired locomotive. It is the story of how a wartime aviation company built the most complex diesel engine the world had ever seen, only to discover that engineering brilliance is not the same thing as industrial survival. Every week we tell the stories of British engines, factories, and industrial names that once taught the country what power sounded like and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in the Napier factory at Acton, in the years just after the Second World War. The story of the Deltic does not begin on the steel rails of the East Coast Main Line. It begins in Acton, West London, inside the engineering halls of D. Napier and Son. By the years immediately following the Second World War, Napier had established a fierce reputation for building machines of terrifying complexity. They were the architects of the Napier Sabre, the 24-cylinder sleeve valve aero engine, an engine built for aircraft use, where power, weight, reliability, and certification mattered differently from road vehicles that had powered the Hawker Typhoon fighter. Napier did not build simple engines. They built high-performance, precision machine solutions that pushed the absolute boundaries of metallurgy and thermodynamics. In 1944, the British Admiralty, the command of the Royal Navy, approached Napier with a problem that standard engineering could not solve. During the war, the Royal Navy's fast patrol boats and motor torpedo boats had relied on high-powered petrol engines that usually use spark ignition to burn a petrol-air mixture. While the American-built Packard V-12s were fast, they were also a severe liability. Petrol in a wooden-hulled combat boat was a devastating combination. A single tracer round could ignite the fuel vapor, turning a fast patrol boat into an inescapable inferno. The Admiralty demanded a diesel engine, an engine that ignites fuel by compressing air until it becomes hot enough to burn diesel fuel, removing the need for highly volatile petrol. But there was a physical trap. Traditional diesel engines of the era were built for tugboats, cargo ships, and lorries. They were made of thick cast iron, designed to run at low revolutions, and were incredibly heavy. The Royal Navy needed a diesel engine that possessed the lightweight power-to-weight ratio of an aero engine. They wanted a machine that hit like a heavyweight, but weighed like a featherweight. Napier accepted the challenge. The design team, led by engineer Ernest Chatterton, knew that a conventional layout would never meet the Admiralty's demands. A standard inline or V-block diesel would simply be too heavy and occupy too much space. They needed to extract the maximum possible combustion force from the smallest possible footprint. The solution they pursued was the opposed-piston layout. An opposed-piston engine is a design where 2 pistons share a single cylinder, pushing towards each other to compress the air, completely eliminating the need for a heavy, complex cylinder head. The upper part of the engine that normally seals the cylinders. To maximize the power cycle, Napier chose to make it a 2-stroke engine, an engine that completes a power cycle in 2 piston strokes, firing every time the pistons meet, making immense power for its size but requiring complex air scavenging to clear the exhaust gases. However, opposed-piston engines usually presented another massive problem. They required 2 crankshafts, the rotating shafts that turn piston motion into rotational power, one at the top and one at the bottom, connected by a heavy gear train. This made the engine absurdly tall and unsuitable for the cramped hull of a fast patrol boat. Napier needed a breakthrough. Napier's solution to the height problem was a stroke of absolute madness and sheer mechanical brilliance. Instead of stacking the cylinders vertically, they arranged them in an equilateral triangle. This was the birth of the Delta configuration, the shape that gave the Deltic its name. The block, the main engine structure that holds the cylinders and major internal parts, was cast in lightweight aluminum alloy. It consisted of three banks of cylinders forming a triangle, with a crankshaft at each of the three corners. Every cylinder housed two pistons, crashing towards each other at the center. In its final marine form, the Napier Deltic was an 18-cylinder engine. But because every cylinder had two pistons, the block contained 36 pistons in total, driving three separate crankshafts that were all geared together at the end of the engine to turn a single output shaft. In the machine shops of Acton, workers who were used to the tight tolerances of aviation engineering found themselves building a marine engine with the precision of a Swiss watch. The complexity was staggering. 36 pistons and 36 connecting rods, the parts that link the piston to the crankshaft, had to operate in perfect mechanical harmony. There were no valves to adjust because the pistons themselves covered and uncovered intake and exhaust ports in the cylinder walls as they moved. If the phasing gear train at the output end of the engine failed, the three crankshafts would fall out of sequence, and the pistons would collide in the center of the cylinders, tearing the engine apart in milliseconds. When the first prototypes were fired up in the test cells at Acton in the late 1940s, the sound was completely alien. Because of the triangular geometry, the crankshafts had to rotate in specific directions, and one bank of cylinders featured a reverse rotation crank. The phasing of the exhaust ports created a continuous, overlapping detonation. It did not rumble like a standard marine diesel, it shrieked. The engineering gamble paid off. The Napier Deltic 18-cylinder marine engine weighed just under 5 tons. A conventional marine diesel of the era, producing the same power, weighed more than 15 tons. By 1952, the Deltic was ready for sea trials. The Admiralty's demands had been met, and the Royal Navy eagerly adopted the engine, installing the howling aluminum triangles into the new Dark-class fast patrol boats and the Ton-class coastal minesweepers. The Deltic proved its worth, pushing lightweight hulls through the water at 40 knots, delivering up to 2,500 horsepower in a package no larger than a standard commercial generator. Napier had delivered exactly what the British military had asked for. But the British engine market was ruthless, and peacetime naval contracts were limited. The Acton factory had invested immense capital in tooling, casting, and developing this triangular anomaly. If the engine was going to survive as a profitable industrial product, Napier needed a bigger market. They needed fleet orders. The Royal Navy had its power, but Napier's triangular masterpiece was about to leave the water, heading for an industry that demanded not just speed, but unrelenting daily punishment. The turning point came because D. Napier & Son was not an independent entity. Since 1942, the firm had been owned by English Electric, an industrial giant that, among its many massive engineering divisions, built railway locomotives. In the early 1950s, the management at English Electric looked at the howling aluminum masterpiece sitting on the test beds in Acton and saw a radical solution to a massive national problem. In 1955, that solution rolled out of the Vulcan foundry in Newton-le-Willows as a single, audacious prototype. It was known officially as English Electric DP1, clad in a striking blue and cream livery with a purposeful, aggressive nose. But what truly mattered was hidden inside the body shell. The engineers had not just installed one Napier Deltic engine to power the traction motors, they had installed two. This meant the DP1 locomotive carried two 18-cylinder blocks. That was 36 cylinders and 72 pistons crashing back and forth in unison, producing an astonishing 3,300 horsepower. To understand why this was a breakthrough, you have to look at the British railway network of the era. In the mid-1950s, the East Coast Main Line, the vital steel artery connecting London King's Cross to Edinburgh, was still dominated by steam, heavily reliant on the aging fleet of coal-fired express locomotives that had held the line since the 1930s. British Railways desperately wanted to modernize, but early conventional diesel engines were heavy, slow-revving, and physically enormous. To achieve the 3,000-plus horsepower needed to haul heavy passenger trains at high speeds, standard diesel builders would have had to make engines so incredibly heavy they would destroy the tracks. The strict British axle load limit, the maximum allowable weight a single set of wheels can put on the rails without cracking the infrastructure, meant that conventional heavy diesels were useless for top-tier express work unless they were run in pairs. And double-heading meant paying for 2 locomotives, 2 maintenance crews, and twice the fuel. The Napier Deltic bypassed this problem completely through sheer power density, the amount of power an engine can produce relative to its physical size and weight. Because the engine had been designed for the cramped hulls of fast patrol boats, it was incredibly light. By installing 2 of these compact, high-revving marine engines into a single locomotive chassis, English Electric created a machine that was light enough to protect the tracks, yet powerful enough to replace 2 conventional engines. It was a brutal, brilliant mechanical shortcut, but it also introduced an immense engineering tension. The marine environment and the railway environment are totally different worlds. In a Royal Navy patrol boat, a Deltic engine ran in short, violent bursts. A fast attack craft might sprint across the English Channel at full throttle for a few hours, then return to a naval base where specialist mechanics could strip it down, check the tolerances, and prepare it for the next sortie. Furthermore, the cooling system had access to the entire ocean. A railway locomotive enjoyed none of those luxuries. A train does not sprint, it grinds. A mainline locomotive would be expected to haul 500-ton trains of steel carriages from a dead stop, accelerating under massive electrical and mechanical load, holding 100 miles per hour for hours on end, day after day, week after week. The engine would be subjected to relentless thermal cycling, picking up brake dust and track dirt, enduring violent vibrations from the steel rails. The Napier engineers in Acton had to adapt their aviation-grade triangle for this brutal punishment. They fitted a complex phasing gear to ensure the 3 crankshafts stayed perfectly synchronized under the sudden shock loads of accelerating a massive train. They had to refine the governor, a mechanical control device that automatically regulates engine speed by adjusting the amount of fuel injected, to prevent the high-revving 2-stroke from tearing itself apart when the electrical load suddenly dropped. The exhaust system had to be redesigned, channeling the deafening noise of 72 opposing pistons up through the roof of the locomotive, resulting in the famous blue haze that would soon blanket British railway stations. The DP-1 prototype spent years proving the concept, logging thousands of miles and convincing a highly skeptical railway establishment that this screaming aviation-derived oddity could actually do the job. The proof was undeniable. The prototype was so fast and accelerated so violently that it consistently arrived at stations early, forcing British railways to hold it at red signals just to keep the rest of the timetable intact. The breakthrough was complete. In 1958, British Railways placed the historic order. Because of the locomotive's immense capability, they did not order hundreds. They only needed 22. These 22 production locomotives, officially designated the Class 55, were built to completely take over the top-tier express services on the East Coast Main Line. When the first production Class 55 rolled out in 1961, finished in two-tone green, it represented a total shock to the British service network. The 22 locomotives were allocated to just 3 major depots: Finsbury Park in London, Gateshead near Newcastle, and Haymarket in Edinburgh. A typical railway depot of the time was a place of coal dust, heavy steel, massive spanners, and slow-moving, simple machinery. Now, mechanics who had spent their lives adjusting the external valve gear on steam locomotives were suddenly handed service manuals for an aluminum, valveless, 2-stroke, opposed-piston triangle that required the cleanliness and precision of an aircraft hangar. The Class 55 was not just a new engine. It was a completely new philosophy of speed. The tracks were laid, the timetables were rewritten, and Britain was about to hear a sound it would never forget. The arrival of the Class 55 Deltics on the East Coast Main Line did not just change a timetable, it changed the physical landscape of British rail travel. By the early 1960s, the 22 production locomotives, numbered D9000 to D9021, had systematically taken over the elite express duties. They displaced the legendary A4 Pacific steam locomotives, the streamlined icons of the 1930s that had previously held the speed records. But steam was labor-intensive, dirty, and exhausting. The Deltic offered a ruthless, modern alternative. British Railways concentrated the entire fleet at just three principal maintenance bases: Finsbury Park in North London, Gateshead near Newcastle, and Haymarket in Edinburgh. From these three depots, the Deltics effectively owned the steel spine of the eastern UK. To understand the scale of this mechanical dominance, you had to stand under the glass roof of London King's Cross Station in 1965. A Deltic idling at the buffer stops was a sensory assault. Unlike a conventional diesel engine that produced a deep, rhythmic thumping, the Napier Deltic produced a continuous, high-pitched scream. Because it was a two-stroke engine with 36 pistons moving in opposed pairs across two massive engine blocks, the exhaust pulses overlapped so rapidly that they merged into a single deafening drone. When the driver opened the throttle to pull a 500-ton train of Mk1 carriages out of the station, the locomotive would shudder, emit a thick canopy of unburnt blue oil smoke, and unleash a howl that bounced off the Victorian brickwork. People standing on the platform felt the vibration in their chests. The drivers who mastered these machines experienced a profound cultural shock. These were men who had spent their entire working lives covered in coal dust, reading the heat of a firebox and managing boiler pressure. Now they sat in an enclosed forward-facing cab, insulated from the weather but situated just feet away from two howling marine aviation engines. When a driver advanced the power controller, there was no gentle buildup of steam. The response was electrical and immediate. The twin Napier blocks fed massive generators, which in turn powered the electric traction motors on the axles. The acceleration was savage. For the first time in British railway history, a sustained 100 miles per hour, 160 kilometers per hour, became a daily timetabled expectation rather than a rare headline-grabbing stunt. The Deltics took over the most prestigious named trains in the country. The Flying Scotsman, the Talisman, the Yorkshire Pullman, and the Hull Executive were all hauled by this screaming aluminium triangle. The journey time between London and Edinburgh was brutally slashed. What had been a grueling all-day expedition was suddenly reduced to just under 6 hours. The engine achieved this not just through raw horsepower, but through sheer power density. Because the engine blocks were so incredibly light, the locomotive carried a lower axle weight than conventional diesels of similar power. This meant it could hit track speed limits and hold them through curves without destroying the steel rails beneath it. But this relentless speed came with a hidden cost. The East Coast Main Line was not the English Channel. In a naval patrol boat, a Napier Deltic might run at full throttle for a frantic hour before returning to base. On the railway, a Class 55 would depart King's Cross, hit 100 miles per hour on the long, punishing stretches of track through Cambridgeshire and Yorkshire, and hold that screaming RPM for hours on end. It would endure the violent lateral shocks of point work, the relentless thermal cycling of braking for speed restrictions, and accelerating back to maximum power day after day in rain, snow, and summer heat. In a Britain where an engine could decide whether an aircraft lifted from a grass airfield, a lorry made its delivery, a motorcycle carried a rider through the night, a bus left the depot, a racing car survived the next lap, or a massive express train kept its high-speed promise to the nation, power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. And the Deltic had earned that trust. By the late 1960s, it was no longer just an experimental oddity. It was the undisputed king of the British railway network, a symbol of a modernizing nation that had finally left the steam age behind. But inside the dark, oil-soaked sheds of Finsbury Park, the mechanics were beginning to learn the true price of keeping an aviation masterpiece alive on the ground. The true measure of the Deltic's dominance was not just its top speed, but its sheer utilization. In the old steam era, an A4 Pacific required hours of preparation, fire lighting, ash clearing, and boiler washouts before it could pull a heavy express train. The Class 55, by contrast, was treated less like a traditional train and more like a commercial airliner. A Deltic would arrive at Edinburgh Waverley, discharge its passengers, run the short distance to Haymarket Depot for refueling and a rapid inspection, and be rostered to head back south to London King's Cross just hours later. Because British Railways had only purchased 22 of these production machines, the fleet had to be worked relentlessly to cover the demanding East Coast timetable. It became standard for a single Class 55 to rack up over 200,000 miles a year, a staggering, unprecedented figure for British railway traction in the 1960s. They accumulated millions of track miles faster than anything else on the network. To the British public, the Deltics quickly evolved from experimental machines into a cultural phenomenon. They were given names that reflected national prestige and power. Locomotives allocated to the Northern and Scottish depots were adorned with the titles of famous British Army regiments, such as the Black Watch, Gordon Highlander, and Royal Scots Grey. Those based in the South carried the names of winning racehorses, including Meld, Pinsa, and Elizabeth. Standing on the platform at York, Doncaster, or Newcastle as a Deltic tore through the station became a defining sensory memory for an entire generation. Whether painted in their original two-tone green or the later ubiquitous British Rail corporate blue with warning yellow ends, their approach was always announced by sound before sight. The distinctive two-stroke drone would echo through the deep brick cuttings, followed by a violent rush of displaced air and the lingering smell of unburned oil from the exhaust ports. But this aviation-style utilization required an aviation-style tolerance for stress. Underneath the sleek body shells, the two triangular engine blocks were constantly battling their own internal forces. The sheer heat generated by 36 pistons detonating diesel fuel in an aluminium block was immense. The phasing gears that kept the three crankshafts from colliding, the intricate exhaust manifolds, and the high-speed scavenge blowers were all subjected to relentless vibration and thermal shock. For over a decade, the Class 55 held the line brilliantly. They were the undisputed masters of the Eastern Route, shrinking the geography of the country and turning the 393-mile run between the English and Scottish capitals into a reliable high-speed commute. The drivers loved the immense electrical power at their fingertips, and the passengers loved the reduced journey times. Yet within the oil-stained floors of Finsbury Park and Gateshead depots, the maintenance foremen were looking at the sheer volume of spare parts required to keep these aluminium triangles firing perfectly. The Deltic had taught the country to trust a new kind of speed. It had not solved what would happen when that speed required a factory to keep it alive. The decline of the Napier Deltic did not begin with a catastrophic failure on the main line or a sudden change in government policy. It began with a small crack in the economic logic of keeping it alive. Inside the oil-soaked sheds of Finsbury Park and Gateshead in the late 1960s, a fitter might notice a subtle change in the pitch of the exhaust, a heavier vibration through the floor plates, or a thicker cloud of blue smoke lingering under the depot roof. These were the early warning signs of a machine tearing itself apart from the inside. The Napier Deltic was a two-stroke engine, and by its very nature it consumed oil to lubricate its cylinder walls. But the opposed-piston layout meant that carbon buildup around the exhaust ports was a constant, creeping threat. If the intricate phasing gears, the critical cogs that kept the three crankshafts perfectly synchronized, suffered even a fraction of a millimeter of wear, the timing would slip. If the timing slipped, the 36 pistons risked colliding in the center of the cylinders at over 1,500 revolutions per minute. This mechanical fragility triggered a devastating collision with the second great force of the British engine market: workshops, dealers, fleets, riders, pilots, and service networks. A railway maintenance depot of the 1960s was built around accessible, heavy engineering. It was a world of thick grease, heavy spanners, and cast iron. If a conventional four-stroke diesel engine, an engine that completes intake, compression, power, and exhaust strokes across four piston movements, suffered a burnt valve or a cracked piston, a mechanic could simply unbolt the heavy cylinder head, reach into the block, replace the broken component, and send the locomotive back to work the next morning. The Deltic afforded no such luxury. Because of its triangular opposed-piston design, it possessed no cylinder heads at all. To reach a single damaged piston, a mechanic would have to completely dismantle the engine block, unmeshing the complex gear trains and splitting the bespoke aluminum castings. This was precision aviation engineering, demanding the cleanliness of an aircraft hangar. It was entirely beyond the capability, the tooling, and the harsh environment of a standard British railway shed. Consequently, British Railways was forced into a punishing maintenance strategy known as repair by replacement. When a Class 55 locomotive developed a serious engine fault, the depot fitters would unbolt the heavy roof panels of the locomotive, bring in an overhead gantry crane, hoist the entire 5-ton Napier Deltic engine block out of the chassis, and drop a freshly overhauled spare engine in its place. The broken engine was then strapped to a flatbed wagon and transported hundreds of miles away, either to the heavy engineering works at Doncaster or all the way back to the manufacturer. While this modular approach kept the locomotive out on the tracks earning passenger revenue, it exposed the first great force of industrial decline: iron, aluminium, fuel, and manufacturing costs. To sustain this relentless repair-by-replacement cycle for a fleet of just 22 locomotives, British Railways had to purchase and maintain a massive pool of spare engines. At times, the railway held a spare ratio of nearly 30%. They were effectively paying to maintain a shadow fleet of incredibly expensive, highly complex aviation engines just to guarantee the daily timetable. Every time an engine was sent back for a factory overhaul, the maintenance bills were astronomical. The engine was brilliant, but the financial architecture required to support it was completely unsustainable. At the same time, the industrial foundation that had created the Deltic was collapsing. D. Napier and Son, the proud wartime aviation firm that had engineered the engine, was steadily losing its independence. By the late 1960s, the company was fully absorbed into its parent company, English Electric. Then in 1968, English Electric itself was swallowed by the General Electric Company, known as GEC. As corporate consolidation swept through British manufacturing, the dedicated artisanal support network that understood the peculiar requirements of a triangular two-stroke diesel began to dissolve. The brilliant engineering eccentricity of Acton was replaced by the cold, rational spreadsheets of a massive corporate conglomerate. The engine still howled at 100 miles per hour. The Class 55 still looked like the undisputed master of the East Coast Main Line. But inside the boardroom, British Railways had already run the numbers, and they had realized a harsh truth. Maintaining an aviation masterpiece on a railway budget was financial suicide. The tracks were ready for the next era of high-speed travel, but the Deltic would not be the machine to deliver it. By the mid-1970s, the East Coast Main Line was facing a new kind of pressure. The expanding British motorway network was stripping passengers away from the railways, and British Rail needed to push journey speeds up to 125 miles per hour to survive. To achieve this, they developed the high-speed train, widely known as the Intercity 125. This new train did not rely on complex aviation triangles. It was powered by the Paxman Valenta, a conventional four-stroke V12 engine that achieved its immense power through aggressive turbocharging rather than opposed-piston trickery. The Paxman Valenta was loud and violent in its own right, but crucially, it spoke a mechanical language that a railway depot could actually understand. If a Valenta dropped a valve or cracked a piston, a fitter at a standard British maintenance shed could simply unbolt the heavy cast iron cylinder head, replace the broken component, and return the train to service. The era of delicate, modular, repair by replacement was over. The British railway industry had learned the hard way that an engine must fit the service network that surrounds it. Faced with the crushing maintenance bills of the Deltic fleet, British Rail made the only logical financial decision. The Class 55 had to die. As the new high-speed trains flooded the eastern route in the late 1970s, the Deltics were systematically stripped of their elite express duties. The howling aluminium masterpieces were cascaded down the operational hierarchy. Machines that had once hauled the Flying Scotsman at a relentless 100 miles per hour were suddenly relegated to dragging heavy, slow-moving parcel trains, overnight sleepers, and stopping passenger runs to Hull or Cleethorpes. This was the worst possible environment for a high-revving two-stroke marine engine. The Napier Deltic was designed to be run hard and fast. The frequent stops, prolonged idling, and low-speed running caused carbon to rapidly build up and choke the exhaust ports. The signature blue smoke grew noticeably thicker under the station roofs. The internal vibrations worsened as the phasing gears wore down. Mainline breakdowns, once a rare embarrassment, became a frequent operational headache. Knowing the fleet was doomed, British Rail management severed the supply chain. The massive financial contracts for major factory overhauls were canceled. When a Napier engine block suffered a catastrophic internal failure, it was no longer transported back to a specialist works to be carefully rebuilt. It was simply pushed into a dark corner of a depot and brutally stripped for parts to keep the remaining locomotives running. The maintenance strategy shifted from preservation to cannibalization. The dedicated fitters at Finsbury Park in Gateshead, who had spent a decade mastering the intricacies of these bizarre machines, were now forced to watch them slowly tear themselves apart. By 1981, the great fleet of 22 locomotives was rapidly shrinking. Their body shells were filthy, their engine bays rattled with worn gears, and they were constantly leaking oil. Then came the scrapmen. At the heavy engineering works in Doncaster, the cutting torches were fired up. The machines that had defined a generation of British speed were dragged onto the breaker's yard. The intricate aluminium engine blocks, the absolute pinnacle of wartime aviation engineering, repurposed for the rails, were unceremoniously sliced into rough scrap metal. The industrial ecosystem that had created them, maintained them, and relied upon them had completely collapsed. The Deltic had not failed because it was weak. It had failed because it demanded a world that no longer existed. The engines grew tired. The maintenance bills climbed. The new trains arrived. The spare parts vanished. The cutting torches sparked. The blue smoke cleared. The sound faded. The railway moved on. When the final British Rail Class 55 was retired in the winter of 1982, the Napier Deltic engine should have vanished entirely from the national consciousness. The corporate entity that created it, D. Napier and Son, had long been absorbed into English Electric, which itself was swallowed by larger conglomerates before the famous name effectively faded into industrial history. The Acton factory in West London, where those brilliant, eccentric engineers had first sketched the triangular layout to satisfy the Royal Navy, no longer built the engines. The East Coast Main Line belonged to the Paxman Valentavas 12, and the nation was looking ahead to the era of electrified railways. But old British engines rarely vanish cleanly. Out of the original 22 production locomotives, an astonishing 6 were saved from the scrapman's torch. They were not preserved by wealthy corporations or state-funded transport programs. They were bought by deeply stubborn enthusiast groups, most notably the Deltic Preservation Society, formed by ordinary people who simply refused to let the most distinctive sound in British railway history die. These volunteers took on a machine that had financially crippled a nationalized railway. They inherited an 18-cylinder, opposed-piston, valveless, two-stroke aviation triangle, a machine that required specialist factory overhauls and perfectly clean environments to prevent its 36 pistons from destroying each other. And they decided they would keep it running in drafty railway sheds and on heritage branch lines. To do this, the preservationists had to rebuild the service network that the government had dismantled. Because original spare parts were no longer being manufactured, they had to become industrial archaeologists. And this led to a strange, surprising footnote in the history of the engine. The survival of the railway Deltics was ultimately guaranteed by the sea. During the Cold War, the Royal Navy and other Allied Marine forces had stockpiled hundreds of spare Deltic engines and heavy components for their fast patrol boats and coastal minesweepers. When the military finally decommissioned these vessels, the railway preservationists swooped in. Complete marine engine blocks were purchased from naval scrapyards, stripped of their saltwater cooling equipment, and heavily modified to fit inside the Class 55 locomotives. The very naval origins that had made the engine so frustratingly complicated to maintain on the tracks ultimately provided the crucial spare parts required to save it. Today, you can still hear that distinct, terrifying scream. Several Deltics are kept in running condition, sometimes hauling heritage tours on the very mainline tracks they once dominated. At the National Railway Museum in York, a beautifully restored Class 55 sits under the lights, a monument to a specific era of speed. But this is not nostalgia. A Napier Deltic idling at a preserved station, trailing its signature blue smoke, is a physical argument about a vanished world of British engineering. It proves that there was a time when the industrial answer to a massive transport problem was not software, not battery management, not hybrid efficiency, and not outsourcing to a global supply chain. The answer was absolute, uncompromising mechanical audacity. The Deltic was the ultimate expression of the internal combustion engine pushed to its geometric limits. It was a machine that required workers in a West London factory to build railway power with the tight tolerances of a fighter plane. It was a bridge between the wartime aero engine and the modern transport network. It failed not because it lacked power, durability, or brilliance. It failed because the economics of keeping such a complex masterpiece alive simply did not make sense in a cost-driven world. The business model died. The logic of the service network collapsed. But the machine itself was magnificent. Somewhere in a British railway preservation shed, an 18-cylinder Napier Deltic block sits quietly on heavy steel trestles. The intricate aluminium casting is dulled by decades of heat and carbon. The complex phasing gears are locked tightly in place, and the faint smell of heavy two-stroke oil still hangs in the cold air, waiting for a sound that the modern transport industry no longer needs to make. See you in the next one.